Hi, this is S. Lakshmanachari, working as Assistant Professor in Department of Cybersecurity, Institute of Aeronautical Engineering, Hyderabad. In this lecture, we are going to discuss the problems on instruction sets. So, basically, the instruction is a command to the processor in order to perform a specific task or specific operation. So, in this lecture, we will solve some problems based on the instruction sets. So, the first problem is, consider a processor with 64 registers and an instruction set of size 12. So, we are considering a processor. So, that processor, it is having 64 registers and instruction set of size 12. That means that particular instruction processor, it is having 12 instructions. So each instruction has 5 distinct fields. So the field, the instruction, it has several fields. So this particular instruction, it is having 5 different fields, namely opcode, 2 source register identifiers, 1 destination register identifier, and 12-bit immediate value. So the instruction, it has total 5 different fields. So the first field is the opcode, and next two are the source register identifier, and the next one is the one destination register identifier, and followed by a 12-bit immediate value. So these are the different fields of the instruction. So each instruction must be stored in memory in a byte aligned fashion. So byte aligned fashion means the instruction, it will be stored in 1 byte or 2 byte or 3 byte, 4 byte, 5 byte, like that. So it will not be 2.5 bytes, 2.6 bytes, so like that. So it will take a nearest integer value. So that is a byte aligned fashion. So in this problem, we are going to find the amount of memory required for a program of 100 instructions. So if the program consists of 100 instructions, then what are the memory size required in order to store the program? So that we are going to find out. So the number of registers are 4. Number of registers are 64. Okay. So one instruction is divided into 5 parts. So already the problem mentioned that so instruction is divided into the 5 fields. So what are those fields? So the instruction format, so this one. So total 5 fields are there. So this is the 5 fields. So the first field is the opcode. First field is the opcode, and next one is the source register. Source register. So RS1, RS2. Source register, 2 source register identifiers, and 1 destination register identifier, or D1 destination register, and an immediate value. So 12-bit immediate value. Okay, so this is a instruction format. Okay, so the opcode, as we have instruction set of 12. So this particular processor, it is having total 12 instructions. So that means the number of opcode bits are required, or it could be a 4 bits, because if you take 3 to power 3, if you take 3 bits to power 3, with 3 bits we can represent the maximum 8 operations. So 8 instructions we can represent. So but this particular processor, it is having 12, the instruction size of 12. So that's why we are taking 4 bits. So 4 to power 4, 16. So that means by taking 4 bits, we can represent maximum of 16 opcodes. 16 opcodes. So that's why we are taking the bits of 4. So 2 power 4, that is equal to 16. So the opcode bit size is the 4 bit. So opcode size is a 4 bit. So using that 4 bits, we can represent up to 16 instructions. So that is the opcode. Okay. So coming to the part 2 and 3. So part 2 is the second field is the source register 1 and source register 2. That means we have two source. So we have two source registers. So here small change. So here you can take RD1, here RS1, RS2. Okay. So these are the destination register and these are the two source registers. So two source registers are there, RS1, RS2. So these two source registers as there are. So in the problem they mentioned total we have 64 registers. So in order to represent every register we require 6 bits because 2 power 6. So 2 power 6 is equal to 64. So that's why we require 6 bits in order to represent every register. So because of two source registers, so 6 bits plus 6 bits. So total 12 bits we require. Okay. And coming to the next one, destination register. So destination register also it is a 16 bit because the number of bits required to represent every register is a 6 bits. So that's why the destination register also we are taking the 6. Okay. And already in the problem directly they mentioned a 12-bit immediate value. 12-bit immediate value. So now the size of the instruction is we have to add. So 4 plus 6 plus 6 plus 6 plus 12. So if you add all those, then you will get 34 bit. So you will get the 34 bit. So but the instructions are stored in the memory as a byte. So that's why we have to divide this number of bits by the 8 so that we will get in a form of bytes. So if you divide the 34 by 8, you will get 4.25. So 4.25 because here this 4.25 bytes we cannot store in the memory because the instructions are stored in the memory in a byte aligned format. So byte aligned format means this 4.5 we are taking to the its nearest integer value. So after 4.5 next integer value is 5. So that's why we are taking the 5. So that means for every instruction it takes 5. It takes 5 bytes. Okay. So as mentioned in the program, in order to store the 100 instructions, the memory required. So that would be 5 into 100 because the 100 instructions are there. And the 100 instructions, every instruction it takes 5 bytes. So total 500 bytes. So 500 bytes is of memory is required to store 100 instructions of the program. So this is a way of solving the first one. And coming to the second one, a processor has 40 distinct instructions. 40 distinct instructions. So a particular processor is having 40 distinct instructions and 24 general purpose registers. A 32-bit instruction word has a opcode, 2 register operands and immediate operand. So the number of bits available for the immediate operand field is okay. So you can see, so total we have 40 instructions and 24 general purpose registers. Okay. So the format of the instruction is, so see, 1 opcode, 2 register operands and 1 immediate operand. That means the instruction here in this scenario it is having 4 different fields. 4 different fields. So the first field is opcode and remaining 2 are the next 2 are the 2 register operands that you can call R1, R2. Next followed by immediate value. Immediate value. So this is the format of the instruction. So as mentioned in the problem, 40 distinct instructions are there. So in order to represent the 40 different instructions, so we require 6 bits. We require 6 bits because if you take 2 power 5, 2 power 5 is equal to 32. That means if you by using 5 bits, we can represent maximum of 32 instructions only. But in the problem, they mentioned 40 instructions, 40 different instructions, distinct instructions. So that's why we are taking the next value. So that is 2 power 6. That is equal to 64. So by taking the 6 bits, we can represent maximum of 64 instructions. Okay, so that's why the opcode field, the opcode, it consists of 6 bits. So opcode, it consists of 6 bits, so that we can represent all these 40 distinct instructions. And coming to the registers, so total we have 24 general purpose registers. 24 general purpose registers. So if total 24 registers are there, the number of bits required to represent every register is 5. Okay, the number of bits required is 5, because 2 power 5 is 32. Suppose if you take 4, 2 power 4, 16. Okay, so 2 power 4 is 16. That means we can access only up to the 16 registers only, but we have 24 registers. So by taking 4 bits, we are not able to cover all the 24 general purpose registers. So that's why we are taking the 5 bits, so that we can access all the 24 registers. So the number of bits for one register is 5 bits. So 5 bits, and for another register also another 5 bits. Okay, and then immediate value. So the number of bits available for the immediate operand field is immediate operand field. Okay, so we need to calculate the value, the number of bits for the immediate operand field. So for this, see, by adding the opcode bits to register operand fields, so 6 plus 5 plus 5. So 6 plus 5 plus 5. So total 16. So as it is a 32 bit instruction. So the problem mentioned, it is a 32 bit instruction. So that means the total size of this is a 32 bit. 32 bit. So this by opcode to operands. So total is a 16 bits. So 32 minus 16. So that is equal to 16. So we have a 16 bit immediate value. We should have a 16 bit immediate value. So this is a way of calculating the immediate value. Coming to the next question, a machine has a 32 bit architecture. So a machine or processor, it is having a 32 bit architecture with one word long instructions. One word. So because of this 32 bit, so it is a 32 bit processor. So it means one word long instruction. So that particular architecture, it is having a one word long architecture. That means one word is equal to, it is a 32 bit instruction length. Okay, 32 bit instruction length. That means the size of the instruction is a 32 bit, and it has 64 registers. It has 64 registers, and each of which is 32 bits long. Okay, so total we have 64 registers. 64 registers, and the size of each register is a 32 bit. 32 bit, and it is needed to support 45 instructions. 45 instructions which have an immediate operand in addition to the 2 register operands. Assuming that the immediate operand is an unsigned integer, the maximum value of the immediate operand is. So we need to find the maximum value of the immediate operand. Okay. So let's go to the solution. So a machine has 32 bit architecture. So already in the problem mentioned 32 bit architecture. So that means therefore it is having a one word instruction. That means the one word is equal to 32 bit instruction size. And as the processor has 64 register, so total the available registers inside the architecture are the 64. So that the number of bits required to access each register is 2 power 6. So 6 bits are required to access every register. And as the processor has 45 instructions, so if 45 instructions are there, total we require 6 bits for the opcode. 6 bits. So that we can access up to the 64 bits. Suppose if you take only 5 bits, 2 power 5, 32. So we can access up to the 32 instructions only. But here 45 instructions are there. So that's why we are taking 2 power 6. So 2 power 6 is equal to 64. Okay. And the total bits occupied by 2 registers and opcode. So opcode will be occupied by 6 bits, and registers, each register requires 6 bits. So we have 2 register operands. So that's why 6 plus 6. So total 18. So by having opcode and 2 registers, so total it is occupying 18 bits. 18 bits. So as the instruction size is 32 bits. So it is a 32 bit architecture. That means the size of the instruction is a 32 bit. So total it is a 32 bits. It is a immediate value. So total size is a 32. So how we can calculate the immediate value? So by subtracting 18 bits from the 32. 32 minus 18. Okay. So total 14. So total 14 bits. So that means the immediate value is it is a 14 bits. 14 bits. So the maximum unsigned value using 14 bits is so we are finding the unsigned value for this immediate the maximum value. We can store the number of bits is 14. So 2 power 14 minus 1. So maximum value means minus 1 we are taking because the numbers are starting with 0. So that's why we are taking the minus 1. So 2 power 14 minus 1. So you will get 16,383. So in the immediate operand field, the maximum value we can store is 16,383. Okay. So this is the maximum unsigned value using 14 bits. And coming to the next one, a processor has 16 integer registers. 16 integer registers. So the registers are named with R0 to R15. So total we have 16 integer registers and 64 floating point registers. They are named as F0 to F63. Okay. So it uses a 2-byte instruction format. It uses a 2-byte instruction format. That means every instruction it takes 2 bytes of memory to store in the memory. So there are 4 categories of instructions are there. That are type 1, type 2, type 3, type 4. In type 1 category consists of 4 instructions. So type 1 consists of 4 instructions, each with 3 integer register operands. So with 3 registers, 3 integer registers. And coming to the type 2. So type 2 category, it consists of 8 instructions with 2 floating point register operands. 2 floating point registers. And coming to the type 3 category, it consists of 14 instructions. Type 3, 14 instructions, each with 1 integer register operand and 1 floating point register operand. So 1 register operand plus 1 floating point register. And coming to the type 4. So type 4 consists of n instructions. So n instructions it consists of each with a floating point register operand. With a floating point register operand. So 1 floating point register operand is there. So in this problem, we are going to find the maximum value of n. So that means we are going to find the number of instructions in the type 4. So this is a problem. Okay. So as already we know, the machine has 2 byte. So the instruction it is having the size of the instruction is 2 byte. So 2 byte means 16 bits because 1 byte is equal to 8 bits. So 2 into 8. So that is equal to 16-bit instruction format. Therefore, the possible encodings are 2 power 16. So that means the total 2 power 16 encodings are there. And as the processor has 16-bit register, okay, so in the problem they mentioned 16 integer registers are there, 16 integer operand registers and 64 floating point integer operands. Okay, so as the integer registers are 16, the number of bits for one integer register is equal to 2 power 4. 2 power 4. So if you take 2 power 4, then that is equal to 16. Okay. And as the processor has 64-bit floating point register, 64-bit floating point. So that means the number of bits for one floating point register is 6 bits. 6 bits is required to access all the floating point registers. So 2 power 16, 6 is equal to 64. Okay. So coming to the type 1. So for type 1 category, having 4 instructions. So in this type 1 category, we have total 4 instructions. So we have total 4 instructions and each with 3 integer register operands. So that means every instruction it is having 3 integer register operand. So that means the total bits required is 4 instructions and each instruction it requires 3 integer register operand. So that is equal to 12 bits. 12 bits we require. So these 4 instructions will consume 4 into 2 power 12 encodings. 4 into 2 power 12. That means we can write 2 power 14 encodings. Similarly for type 2. So type 2 total it is having 8 instructions with each having 2 floating point register operands. So already you know, in order to represent the floating point register operand, we require 6 bits because so total floating point register operands are 64. So that's why 2 power 6 that is equal to 64. So total register operands are 2 floating point register operands and each register it requires 6 bits. So 2 into 6 is equal to 12 bits. Okay. So the number of total encodings required are 8 into 8 is the number of instructions into 2 power 12. So that is equal to 2 power 15 encodings. Coming to the type 3. So type 3 category having 14 instructions. Total 14 instructions are there, each having 1 integer register and 1 floating point register. So for 1 integer register, it requires 4 bits and 1 floating point register, it requires 6 bits. So total 10 bits are required for both the integer and floating point register operands. So total instructions are 14. So 14 into, so total bits require 10. Okay. And the total number of encodings are 14 into 2 power 10. That means 14,336 encodings are required. And coming to the fourth type, that is in fourth type we have a number of instructions are n. So in type 4 the number is not mentioned. They mentioned n number of instructions are there. So we need to find what is the value of n. Okay. So in type 4 category instructions, the number of encodings left is so 2 power 16 minus 2 power 14 minus 2 power 15 minus 14,336. Okay, so these are the remaining encodings left. Okay, so this is equal to so total number of instructions are n into so see for type 4 what we are using a 1 floating point register operand. So for 1 floating point register we require 6 bits. So that means the number of encodings required is 2 power 6. into total number of instructions in the type 4 is n. So and the total number of encodings left is 2048. Okay, 2048. So if you solve, the n is equal to 32. N is equal to, so 2 power 6 means 64. So n is equal to 2048 by 64. So you will get 32. So that means the number of instructions in the type 4 is 32 instructions. So 32. So n into 2 power 6 is equal to 2048. Okay. And coming to the next one, explain the mapping procedure to calculate the first micro instruction address for the following operation codes. So here they have mentioned the operation codes. So the computer instruction opcode is mapping with the micro instruction address. Okay, so this is a mapping procedure. So we have a computer instruction. So the size of the computer instruction is a 16 bit. 16 bit. So 0 to 11 are the address. It represents the address of the operand, and 12 to 15. So 12, 13, 14. So total it is a 4 bit. 4 bit. So 4 bit means 2 power 4. That is equal to 16. So we can represent total 16 operations. 16 opcodes we can represent using these 4 bits. Okay. So when we are mapping, see, the first bit will be we are taking as a 0, and the last 2 bits also we are taking the 0, because the micro instruction address is a 7 bit size. So that's why we are adding 10 to the left of the opcode of the computer instruction, and we are appending 2 more zeros to the right side of the computer instruction opcode, so that we will get the 7-bit micro instruction address. So now we are going to see mapping of the computer instruction with this micro instruction address. So opcode given is 0010. So that is the opcode given. Okay. So 0010. So consider the operation code 0010. So we are considering the opcode 0010. So we are placing 0 to the MSB, left of the MSB of the operational code. So we are placing 10 to the left side, and we are adding 2 zeros to the right side. 2 zeros to the right side, so that it will become. So the number of bits in this micro instruction is 7 bits. 7 bits. So see here. So 0010. So this is a opcode. So to the opcode, left side we are adding 10, and right side we are adding a 2 zeros. So that this is a micro instruction address. Coming to the 1011. So similarly, so the same operation 1011. That means we are adding 10 to the left side and 2 zeros to the right side, so that it will form a 7-bit micro instruction address. So this one 0101100. And coming to the last one, 4 ones 1111. So this is a micro opcode of the instruction. Okay. So for this, I am placing 10 to the left side. So MSB I am placing as 0, so that it will become 01111. So to this, I am place 2 least significant bits of the operation code must be appended with 2 zeros. So 2 zeros. Hence the required micro instruction address is 0111100, which is the value 60 in decimal. So this is in the binary. So if you convert this value into the decimal, you will get 60. So in this lecture, we have discussed various problems on the instruction sets. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.